Hi, my name is Britt Bowie. I'm with OMC Hydrogen. I'm here today to talk to you about production of low-cost green hydrogen and syngas using heat and low-cost domestically abundant materials. Our process can use a variety of thermal inputs, either from concentrating solar power, renewable electricity, or even any portion of waste heat. This goes into our isothermal thermochemical redox process, which can simultaneously be fed carbon dioxide and water and split both of these reactants to make a product stream of syngas, or carbon monoxide and hydrogen. Syngas has more than a century of commercially mature technologies behind it to be upgradable into a wide range of useful hydrocarbons, including sustainable aviation fuels, methanols, lubes, and other products. In lieu of this process, we can also take the same exact reactor, the same active material, and simply feed water and create green hydrogen. Our value proposition is simple. It's low cost. Our redox reaction operates isothermally, which allows world record-beating efficiency. In fact, we are in a campaign right now where we will publicly break the world solar to fuels efficiency record. We have no catalyst to foul, so there's no need for rare earths, cobalt, platinum, palladium, yttrium, iridium, or foreign factories to build thousands of modules to reach commercially meaningful scales of production. This, as my CSO puts it, is an iron and aluminum sandwich that scales. So the reactor itself is made of steel. It's refractory lined with alumina, and the active material itself is an iron aluminate. So domestically common, low-cost material. We can tailor it to local resources, that is, CO2, water available, and what kind of heat might be available at the process site we're working at. This all results in 50% less CapEx than current approaches to these products and 30% less OpEx or greater. To take a look across the board in syngas technologies, there's only one that stands here on the left, and that's us. In a single reactor, in a single step, makes syngas. More commonly, you see the middle, which is reverse water gas shift reaction, which goes through the expensive process of low temperature electrolysis, which is then fed into a reverse water gas shift reactor, where a lot of this hydrogen is consumed from the electrolyzer. And then there's a separate penalty in complexity, not only for an additional reactor, but also for the process energy inputs required to run that reaction. Even further to right, much more expensive and less commercially mature is separate electrolyzers, one to reduce CO2 and one to split water. When we look at the potential product markets for this, in short, they're huge. There's a massive current demand for hydrogen. If we look at hydrogen and fuels, it's in excess of a $200 billion a year market. Our serviceable obtainable market is over $400 million a year. And that would just be the California market for hydrogen in renewable diesel refineries. So when we look at where we would go with this for a beachhead market, we would integrate with renewable diesel refineries positioned to serve the California markets. The reasons for this are simple. Renewable diesel requires much more hydrogen per barrel than fossil fuels do. It allows us to scale our reactor up. This is smokestack chemistry. If you want it bigger, you make it bigger. You don't need to stack thousands of modules. The intrinsic to the process of cracking fats, oils, and greases is excess heat created. And there's no storage issues. We don't need to wait for something that uses hydrogen to surface to make our business plan viable. It uses, it distributes into a fuel that is already widely used. That fuel itself, demand is expected to grow at over a 13% compounded annual growth rate, where the hydrogen need to serve that will be in excess of 475,000 kilograms a day by just 2024. From there, we can expand into other markets, including ammonia and power to liquids using this process. The projected earnings, if we look at the projected EBITDA in our business model, which would be to go through the first commercial and then license out an additional 20 facilities by 2032, where most of that is just fed back into a refinery serving low carbon fuel markets. 10% is sold in the FCE market. We have nearly $500 million in EBITDA by 2032. As for investment potential, the technology was developed at CU Boulder, where it attracted over $11 million in grants. OMC Hydrogen was formed around exclusive use license to those patents developed there. We've raised $2.15 million in date, including $1.75 million closed yesterday. This will fund us through pilot design, and we are formalizing partnerships with some high quality partners. Our most common question is, when can we sign an offtake? As for the team, I have extensive experience in renewable fuels, which allows me access into those markets. The engineering team at CU Boulder is the world's leading experts in this technology. And Dr. Wells has multiple early exits and worked across many sectors of business.
We are at time, Britt. Great job. Do we have any questions from our reviewers?